Question 3. The diagram below shows stages in the transmission of a nerve impulse, and you've got a nice little diagram of the membrane potential and various points on this. Okay, so at 1, you're told that the membrane potential before the nerve impulse is initiated. 2 is the stimulus, binding of a neurotransmitter to a ligand-gated sodium channel, and then you've got at 3, the sodium channels are open. At 4, the sodium channels are inactivated. At 5, you've got your potassium ions channels opening, and then at 6, you're back to your resting potential. Okay, which actually is the answer to the first question. State the term that describes the membrane potential at points 1 and 6. That is the resting potential of the cell. Okay, use the diagram to calculate the change in membrane potential between points 1 and 4. I genuinely thought this was a gift of a question. Okay, so at 1 it's minus 70, and at 4 it's plus 30. So in total you've gone from minus 70 to plus 30, so that is 100 millivolts. That's it. Okay, part 3. Use the information in the diagram to explain the importance of the K+ channels, so potassium ion channels, in nerve transmission. Okay, so let's find where the potassium is involved. It says voltage gated potassium ions channels open at 5. So what that is doing is returning the potential to where it should be. So it's returning membrane to resting potential. Sorry, shouldn't use the word not membrane in there. Returning the cell. Okay, so that's what it's doing, but then you're going to have to see how that actually does that. So what you should know is that nerve transmission is all to do with your sodium-potassium pump action. Okay, so what you've done is you have pumped potassium ions into the cell so that they're at much higher concentration inside than outside. So as soon as I open the gates for this one, so if I've got our little cell with our little gates in here, okay, and this is the in and this is the out, this will be a high potassium ion concentration because we did that when we set up our membrane potential, and this will be low. So as soon as I open up this gate at all, okay, and we now have a passage through here, as soon as I do that, I'm going to get potassium ions flowing out through this, and that is going to reset it. Okay, so that's your second mark, or your first mark, depending on how you did that. Okay, so the high potassium inside, when the gates are opened, flow out, changing the charge inside the cell, returning it to its resting potential. Okay, you can use the term repolarization or polarities if you like. Tetrodotoxin is a poison found in some fish such as pufferfish, which has its effect at stage 3 of the process shown in the diagram. Suggest a possible mechanism for the toxicity of this substance. Stage 3. Stage 3 said the voltage gated sodium channels are open. Well, so possible mechanism is to prevent your sodium channels opening. That's basically what you're going to go with. There's no, either it's blocking the channels entirely, so they can't function, or it's just stopping the channel opening itself. Okay, that's it.